topic of my lecture is about precise magnetometers for geophysics and metrology, and it will be really about these two particular fields, and actually I will focus on two particular sensors which are well suited for this application. Just a few words about the geomagnetic field and the observations. The key property is that the magnitude and the orientation of the geomagnetic field vector is not stable in time. And unfortunately, or very good for our applications, is that the time scale goes from hundreds, thousands of years, which would be magnetic reversals, but it goes all the way to milliseconds. And there are interesting phenomena which are happening mainly in the region of our interest, of the interest I'm focusing on in my talk, which is between 1 millihertz and 1 hertz. So in this, I'm calling it ultra-low frequency range of the geomagnetic field spectra, we see the effects of solar storms. We see which can be up to 100 nanotesla peak of magnitude. And when I'm talking about 100 nanotesla, it means this magnitude comes from a stable field from around 44,000 nanotesla. So these pulsations are very small in magnitude and also very small in power, which we can see on the left-hand axis. The pulsations which are lower, even lower in amplitude than effects of solar storms, are happening on a more ordinary basis. So the observation of them can help us a lot in some applications. And there are, of course, the field is not stable at all. There are, of course, some ultra-low frequency oscillations which are occurring like throughout the day. There are other spectral regions like above 1 hertz or below 1 millihertz, which are also interesting for other studies, mainly in geophysics, but I'm not focusing on this range in my talk. I'm focusing on 1 millihertz to 1 hertz. And now the motivation for a precise, I would say, vectorial magnetometer measuring the magnetic flux density, magnitude, and orientation in the ULF band. The ultra-low frequency pulsations provide us basically a free excitation. And this free excitation, because it happens at such low frequencies, the electromagnetic wave can penetrate very deeply in the Earth's field geology profile, so it's used in industry in mineral prospection. Also, observatories which are monitoring the Earth's field and its variations are monitoring ULF pulsations and doing studies of the connection of atmospheric and ionospheric effects on the geomagnetic field. And probably we can, and I will show, we can use these effects also in metrology applications. The typical observatory sensor, which measures, again, not only magnitude, but also the orientation, would be a second harmonic fluxgate. There was a talk a few months ago by my colleague Wojciech Petrucha. Basically, the observatories are focusing very much on the accuracy, not much on the precision or, let's say, low noise of the sensor, but accuracy, calibration, establishing the true orientations of the vector matter. And our goal is once more shown in this picture, where we have in the gray zone basically the power spectra of the Earth sphere fluctuations. The upper limit is summer afternoon, like more noisy day, and the lower limit is quiet times in the morning. So basically, we would like to have our sensor performing at least with this curve, and if we would have the magnetic field noise of our sensor reaching these limits, we would have, of course, only 0 decibel signal-to-noise ratio, so we want to push the noise much lower. Typically, those sensors which are used are part of the second harmonic fluxgate, which is quite noisy. We can see it here, that the noise tends to go up with 1 over f, and here it's actually higher than what we want to observe. Sorry. Those sensors would be either an induction coil, the red curve. The problem of such low noise induction coils is that they are bulky, that they are large in dimensions, and we need, of course, 3 of them, so it's even bulkier. The other sensor we could use is a superconducting SQUID, and we have 2 types in here, the low temperature one, the 4 Kelvin one, which is the bottom blue curve, and high temperature SQUID working at 77 Kelvin. And this is basically our target. We want to reach the noise with our sensor in this region. Basically, we want to be the same in performance as the HTS SQUID or the coil, or of course, even better. So this talk will be basically a competition between HTS SQUID and a fluxgate. And here you can see a size comparison of them. So at least we are not like in 2 orders of magnitude scale difference, but still, of course, a SQUID can be a much smaller sensor. It doesn't really matter in our application, the size difference, because we are measuring fields which are very homogeneous. But for example, in in biomedical field, it would matter. These pictures come from the publication we did in 2019. Dr. Petrucha has shown that with second harmonic fluxgate, there is a limit about 2.5 picotesla per square root of hertz, and the basic problem of lowering this noise further using this technology is the repeatability of the result. And we have moved, and I have been there in the development with docent Buta, who is main author of the magnetic wire and its annealing. We have been working there like since early 2015, 2016 or something like that. And the biggest difference between the second harmonic fluxgate and the fundamental mode orthogonal fluxgate we are using is that we can lower the noise because of a different principle of operation. So instead of exciting the sensor to saturation and back, we are using here quite high DC component with an AC component of excitation, which goes through the ferromagnetic wires. And because we don't have any, or at the best case, we don't have any domain wall movements or reversals, we are only rotating the magnetization so we can get rid of most of the noise. The key, of course, the key point to reach lower noise than originally Sasada had, like it was about 10 picotesla, is to select the proper material, probably anneal the core. And we have found that not only the annealing, which we can see the result on the right-hand side from a remote observation, but we have found that the ultra-low frequency noise of this orthogonal first harmonic fluxgate depends very much on temperature instabilities. And with proper thermal damping, we were in the first step able to reduce the ultra-low frequency noise about 3 times. Of course, it wasn't that easy. There are many effects like magnetoelastic coupling and so on, so the material properties were critical. We have published this, and we have a European patent, which is basically based on this finding. The further improvements, mainly in the electronics, which was like my key contribution, of course also in the sensor design, allowed us to reach a milestone of 1 picotesla per square root of hertz. This milestone of noise is something like a benchmark for geomagnetic field sensors. we have verified that with such a low noise sensor, by subtracting the outputs, we can actually observe the magnetic field originating from the heart, from the currents flowing in the heart muscle. And when we compare it with the ECG, we saw very nice correlation, and also the noise is very low. So basically, it's about 3 picotesla RMS on this picture. The yellow line, I'm sorry for this, is a difference between the two magnetometer outputs. And this brought us to further applications of the magnetometer, where we can actually use the very low noise at very low frequencies. The key, the most important thing to think about is, however, that it's not only the sensor itself which provides us the actual noise floor of our measurement, is also the data acquisition. And I'm illustrating here on this picture that if we measure at very low field range, we can reach very low noise. But in an Earth's field, which would be the green line, of course, we have to employ some techniques to keep the noise low. One of the technique would be, of course, selecting very low noise ADC, but the demands are very high, and mainly at this very low frequency range, the excess noise plays a role. We can see here already excess noise of 0.1 volts data acquisition. So we have chosen this path to compensate the most of the bias here in the field, in the voltage, with a very low noise DACs, and we have actually presented the latest results at the conference a few weeks ago. There is another interesting effect, or I would say interesting, but not very applicable to our field of study. It's the magnetic after effect. And the after effect occurs actually if we expose the sensor, the ferromagnetic wire, to a large external field for a longer period of time. Basically, what happens that the offset of the sensor changes, and it depends on the amplitude and on the duration of this exposure. The sensor settles back to its original value with very large time constant. So this is a slight disadvantage of our sensor if we want to save power, switch it on and off, or if our compensation loop is out of range, we might have to wait several hours to reach the original values. And we have published this in 2022. That would be the basics about the orthogonal fluxgate before I go to further pushing the performance limits down. And the other sensor I was working with and I could compare to our sensor is a SQUID, which is a superconducting quantum interference device. And I was dealing with high temperature SQUID, working at 77 Kelvin in a liquid nitrogen cryostat. Basically, very macroscopic. The SQUID is a superconducting loop with two weak links, two Josephson junctions, which is biased by very low current, roughly in microamps. It was introduced in the 90s. The problem is that the material is quite fragile and the noise is still much higher than 4 Kelvin SQUIDs, but it's very cheap to operate because liquid nitrogen is available in quantities. And from the very basic about the superconducting loop and biasing, we can see that the flux is quantized, and if we bias properly the SQUID loop, we are modulating the critical current of a Josephson junction, and we have a periodic change of output voltage, which I'm showing here. This is actually a picture from a lab course of modern sensors or advanced sensors we are presenting to the students so that they can really put hands-on on a superconducting sensor, on a quantum sensor of magnetic field. The SQUID is, of course, a sensor of a flux, so it really depends on the area, what will be the sensitivity or what will be the distance between the two fundamental quantums. So I'm showing here, for example, in the earth field range, if the B0 would be 200 nanotesla, basically the characteristics repeats every 200 nanotesla on the x-axis. Such a sensor has one problem, that really the distance between the fundamental quanta is very high. So we are employing the classical trick how to linearize the sensor to use a compensating feedback flux loop. We will choose the set point somewhere with the highest derivation, and with this simple, basically I controller, we can compensate the measured field, we can compensate the flux, threading the SQUID, and read out the current needed to compensate such flux. This is the big advantage of the SQUID, because we can have much lower requirements on the data acquisition, because our FLL range can be only few quantums, for example, 400 nanotesla or 1 microtesla easily. The rest of the flux is basically frozen. There are some disadvantages. So, for example, the flux loop must be very fast, because the SQUID is sensitive up to terahertz. And what are the noise limits in industry? This is from the CSIRO from Australia, from their leaflet in 2019. We can see that the noise is very low. It's about 100 or 400 femtotesla at low frequencies, or already low frequencies, but what does it mean? It's 10 hertz. And most of the data sheets or the manufacturer data don't give you noise below 1 hertz, for the reason that in the Earth field, once we are operating the SQUID not in a shielded room, but in an Earth field, we are cooling it down in non-zero field, and due to the imperfections in the material, there is flux trapping, and we have 1/f noise in the IPCO, in the superconducting film. So it really matters, the B cooling and the superconducting quality really matters for 1/f low frequency noise, which is not shown here. There are some limits published, however, so we could take this figure as our goal. So we want to reach something around 5 picotesla per square root of hertz at 100 millihertz. And how did I come to a SQUID? Actually, for my postdoc studies, I spent 1 year at the Stellenbosch University and South African National Space Agency, where they were operating such a commercial SQUID. And from our initial measurements, we have found that basically the SQUID is much noisier than our orthogonal fluxgate, which we brought with us. And this brought us a question: if it's like the property of our sensor being that perfect, or the SQUID having such bad performance. And we have actually found that this SQUID has still quite high B0 quantum of magnetic flux density, and it really suffered from flux trapping, raising the 1/f noise, which we can see here in the time domain. So during those few years, we actually replaced it, and we managed, with the help of my student Michael Dressler, who spent his doctoral studies mobility there, we managed to make the system running 24/7, and then we were able to assess the performance of the SQUID. We have found one interesting effect, which we published and consulted with the manufacturer, and we actually found that there is no cure for it. The SQUID, the high sensitivity SQUID, suffered from ultra-low frequency oscillations, about 2 nanotesla, peak at 5 millihertz. And while this is not a problem in the primary application, for example, biomedical measurements, this is a problem for space weather observation or for exploration, because 5 millihertz is unfortunately exactly in the frequency band where we want to measure. We did a long-term study, and we have actually found that this effect diminishes as the dewar goes empty and starts only a few days after we refill the dewar again with liquid nitrogen. So basically, it had to correspond somehow with the liquid nitrogen cryostat and with the dewar properties. We have found almost perfect coherence between the SQUID output and the dewar bath temperature. Of course, it's not perfectly 77 Kelvin. There is also fluctuations. There are also fluctuations, and we were able to monitor those fluctuations with very high precision. And we have found that this effect was actually reported before for another study where it was proposed to be a thermoacoustic resonance in the dewar. And basically, Blundell was showing the same with the amplitude about 20 millikelvin peak. So our is smaller, but it yields higher noise for our SQUID. And we have verified this again, even in another dewar back at the faculty, and we have published this in a recent article. And now the key point is, of course, how to estimate the noise of the SQUID and of our orthogonal fundamental mode magnetometer in ambient field. Because if we measure in a shield, we are forgetting about some effects like flux trapping in an ambient field or expansion of the dynamic range for the orthogonal fluxgate. Our approach was quite simple to calculate the cross-power spectral density, and we can get the correlated part, which would be the noise of the field we are monitoring, and then by spectral subtraction, we could probably, with some assumptions, obtain the noise of the two individual sensors. So that would be SQUID, that would be the orthogonal fluxgate. Of course, the most important assumption is the signal is stationary. So after assuming that these cross terms, and I'm saying are not negligible, but these cross terms their effect would diminish with large number of averages, we can really obtain the noise spectra of the individual sensor. The problem with ultra-low frequencies, of course, that we have a need for very long records, because the effect of the cross terms decreases only with square root of the number of averages. So it really takes us to get very long data to access the performance. But we did it nevertheless, and this would be the two individual noise spectra for the two individual sensors. And if we calculate the cross-power spectra, we have the yellow line. If we subtract, we can see the noise of our orthogonal fluxgate. And the most interesting thing is that finally we can see the white noise of our DAC compensation. The DAC compensates most of the stable bias in the field so that we can expand the range. So this is the white noise of our DAC, and here we can see 1/f slope, which combines the data acquisition and sensor noise. At 100 millihertz, everything was fine, was corresponding also to what we have measured and recalculated in a shield in a laboratory. But at 0.01 hertz, at 10 millihertz, we have seen like larger values up to 5 times than what we have measured. For the SQUID, unfortunately, we have the effect of the 5 millihertz and 10 millihertz oscillation, so we would need to do another recording or try to mitigate the oscillations of the SQUID with, for example, lowering the temperature of the bath. Nevertheless, at least at 100 millihertz, we can really see that our orthogonal fluxgate reaches the SQUID performance or is even slightly better. Now, we were thinking, why do we see the excess noise? Why is this slope higher than what we would expect? And we have realized that it's actually due to temperature dependence of the output of our sensor. Because every sensor is unfortunately a sensor of temperature, and magnetic field sensors tend to be drifting in temperature, not only with sensitivity, but also with their magnetic offset. And for the orthogonal fluxgate, the dependence was quite high, about 10 nanotesla per Kelvin. So the solution how to do this, of course, is decreasing the temperature coefficient by improving the processing of the signal and improving the material processes. This is something, properties, this is something which is ongoing. But we decided for a simple trick, we decided to add thermal mass, which allowed us to decrease the temperature fluctuations at 10 millihertz, roughly by 1 order of magnitude. And we could really verify that with the outside temperature fluctuations, we were really seeing the excess noise which we saw before. So now we have our sensor, which is the slight yellow line here, embedded in this high density cube. And after we have manufactured like a batch of 10 sensors, we are ready for actual field measurements and to assess the noise of such an improved sensor in a real environment. And I have 2 slides more about precise magnetometer in low field metrology, because this is the other topic of my talk. And we have actually tried to improve the coil systems which are existing at the National Metrology Institute. And our approach is not to use a closed loop sensor or a distant open lead sensor, for example, 50 meters away. Our approach is to use 2 sensors close apart, recalculate and realign the 2 sensors, orthogonal frames together by using actually the ambient noise. And this is the ambient noise we can see here at the faculty, and after our compensation was working, we could reduce it approximately by 1 order of magnitude. We have published this, and we have also shown that these disturbances, either coming from far anthropogenic sources or coming from geomagnetic storms, can be also used for aligning the sensors, mutually aligning the magnetic field sensors. And because metrology is focused on traceability mainly, I am showing here that the flux density standard for the Czech Republic is actually a solenoid on a quartz core. And even though it's calibrated against the primary standard at the Metrology Institute working on nuclear magnetic resonance, the anthropogenous noise at Czech Metrology Institute is very high, and it doesn't allow us to go with the calibration to the original values, with the calibration uncertainty to the original values achieved in the 1980s. So this number actually got worse by 1 order of magnitude. So we are collaborating with the Czech Metrology Institute. We have provided them with very stable current sources. And also we have developed a very low noise nulling sensor with very low range, where the only requirement for it is the 0 stability in a short time. So we can see here like a cross calibration of 2 coils against each other, utilizing the 0 sensor here. So if we compensate the 2 fluxes of the 2 coils, and if we record the currents, we can establish the constant of the second coil to be calibrated. And while I was doing these trials also at the Space Agency in Hermanos, we have found by using only the Earth's field and proton magnetometers or the calibrated coil system, we were actually really able to achieve uncertainty which is like 3 times lower than what Metrology Institute is providing us. So, as the title of the slide is saying, we are trying to bring the precision back home, and we are now a part of a European grant of Euromed with the name European Infrastructure for Low Magnetic Field Metrology, and the role of the CTU is to establish a new call system in Průhonice and establish a disturbance cancellation system utilizing basically the idea we have published in this article. So, summarizing my talk and my achievements in the field, let me switch the order. So, in the scientific field, I think our biggest achievement was to really reach the limit and actually cross it of 1 picotesla noise. And we have shown also the benchmark measurement of unshielded magnetocardiography. That would be this article from 2019. Also, a lot of citations gained my contribution to the field of precise calibration methods for triaxial magnetometers. So that will be one of the fields of study during our metrology grant. And the third one is the chapter in a high-sensitivity magnetometers book, where I basically summarized the efforts how to bring the parallel fluxgate noise low, and I have shown that the noise limits are really somewhere around 2.5 picotesla, and we need to move to another principle, which were the topic of this presentation. So there are some grants, and here are
I think you don't need to go into the details. We will discuss it later. Thank you very much for your thorough and in-depth of the topic focused presentation. And now I open the discussion. And I would like to ask for questions from the auditorium to the subject of the lecture. Maybe if I may start. You said that your work is in collaboration with your colleagues, Associated Professor Buta Petrucha and your student Martin Dressler. Could you please summarize what is your main contribution in these works?
Yeah. The brief summarization would be that my focus is the electronics for the orthogonal fluxgate and the data acquisition performance, basically bringing the sensor out of the laboratory to the field. And Michal Dressler, as a doctoral student, is helping a lot in this field.
Thank you.
Now.
So, any questions? Everything is clear? Okay, if there are no questions, so the last call. Yeah, maybe Professor Havlena.
Magnetometers are sometimes part of the inertial measurement units for navigation, for localization. You mentioned that the magnetic field is very unstable. So is it possible to predict somehow the values so that it is really useful for navigation and localization?
Yeah. At least on the daily scale, the diurnal variation can be predicted. So if we know that the magnetosphere is like quiet, there were no solar storms and the effects are not arriving yet, to the Earth, we can really rely on forecast of the magnetic field orientation of the declination of the inclination. It really repeats on a daily scale. Also, there is like seasonal variations, but these models actually exist. Yeah.
Thank you. Any other questions? Professor Havran.
If you do the calibration between two instruments, how much it is important to put them exactly on the same place? Because if you want to have the same magnetic field, and the outputs from that should be equivalent, so even if it's 1 meter apart, I would already assume that is different magnetic field over at different place. Or if you orientation of the device.
The good point about Earth's field, if it's not disturbed by ferromagnetic objects around, that it's very homogeneous on a very large scale, so a few meters apart is actually almost perfect homogeneity. The problem is once there is anthropogenous noise. So, for example, DC currents from, I don't know, here from the subway or from trams. But even those effects, if we are far enough on a meter scale, we could, to very large extent, assess as homogeneous, and we can compensate. And so, for example, there was a limitation of placing the sensor here. So at our faculty, our sensor had to be a few meters apart, or maybe like 2.5 or something. And still, if my colleague opened the door, which I'm not showing here, we would have a large peak here, because that's the gradient. We cannot really compensate. But in the topic of our metrology grant, we will try to compensate and measure the gradients. So at least the axial gradients, the three gradients, we can really easily compensate in the curl system. We will be measuring, and we will be also compensating for the gradients.
Thank you.
Thank you, and Professor Svoboda.
Okay, just quick technical question. Following the question of Professor Havlena, but if I understand well, that the local disturbances caused by the high voltage power lines and all this kind of stuff is actually more intensive than the day variations you measure, right? But you mentioned that you can, in principle, increase the accuracy and maybe even precision of the IMUs, but this probably concerns the very, very, very expensive IMUs that are used in specialized aircrafts, all this kind of stuff, not really the ground vehicles. Am I right? Or
it's not only ground vehicles. There is now a very hot topic of trying to navigate UAVs only using the Earth's field maps and real-time compensating for the diurnal variations. The good point is you are always flying above your power lines and above the disturbance. And the good point about the disturbance is if it's a current uncompensated, it just decreases by linearly. But if the disturbance is caused like by a point source,
okay, I'm getting it. That's why I was asking about the aircrafts, because I know about some very, very expensive IMUs that can do interesting things. But
thank you. And Associated Professor Straka.
My question is related to the navigation. So I'd like to ask if this kind of sensors can be used to navigate using the magnetic field maps.
Yeah. So actually, I was talking about the orthogonal fluxgate and about the SQUID. So of course, SQUID is out of question because we need to fly it with a cryostat. The orthogonal fluxgate might be used, but our main problem is these two values. It's the offset, the absolute value, and temperature drift of the offset. So this actually disqualifies this sensor for navigation. So for navigation purposes, I would really think that less precise but more stable second harmonic fluxgates, which were presented here a few months ago, are the key to go. Yes.
So if there are no any other questions, let me thank you, the lecturer, and you, the audience, for putting questions. I close the discussion session. Habilitation procedure will continue in the room number 80 in a few minutes, and I would like to ask candidates, members of the committee, reviewers, and head of the department of the candidate to join us.